Hello, my name is Henry Jordan. I'm working under the supervision of Professor Narayanyan Menon, and I will be discussing today simplified Capstan systems as a bridge to understanding networks of flexible filaments. Yes, so what's some motivation for that title and why does it make any sense? Why is it relevant to anything? So most objects that you interact with in your everyday life are held together by internal attractive forces. For example, this would be this metal cube on the right here. It's held together by the ionic bonds within by the metallic bonds within the object. This is also true for lots of other objects in everyday life. But there's also another class of objects which stay together even in the absence of these attractive forces. An example of this are weaves. Weaves are instead held together by the friction at each contact point. And in our first initial investigation into this class of objects, and more specifically weaves, we'll be investigating how this contact friction works and if it has any weird special properties. So to begin, I'll introduce something known as the Capstan effect. The Capstan effect basically relates the force applied at one end. If you take a rope and you wrap it around a rigid cylinder, it relates the force applied at one end to the force registered at another. It obeys the equations at the top and the bottom. The top equation is the case of static friction. The significant thing there is the inequality that develops. And as you can see, it scales very quickly as wrapping angle increases. And this is, for example, why in the picture, one of the most common uses of capstans is in the shipping industry, but the person is able to apply a very small force to the rope, and because of this amplification of the tension due to the wrapping angle, it's able to support a very large amount of tension with the boat docked. It's like this tiny force, when amplified, is able to support the force generated by the entire boat, which is very substantial. And we postulate that each of these interactions in a weave can be viewed as some sort of Capstan equation. It would be modified to some extent because there's many of them. There's some other strange things, but we view that each contact interaction can be viewed as individual Capstan. That's our postulate, and that's what we're looking to test. Yes, but this, as you can see from this picture, the system is really complicated. There's many interactions between many Capstans, and there's lots of downstream effects because the tension force is different at each point, and so yes, it gets very complicated. So we're going to very much simplify the system in our initial investigations. So what does our initial investigation look like? So we basically took 3 rigid capstans and combined them to see if there's any strange effects that generate when there's multiple capstans involved in the same situation, or whether or not they just add as you would anticipate. And we, using a motion, and we first focused on a situation where kinetic friction was the only friction force involved. And we had a known mass hang over a pulley to apply a known force to the right side, and a force sensor attached to a motion device on the left, which could move and induce motion over the capstans and cause the kinetic friction while simultaneously reading the force. And this is our initial data for those tests. The red lines are what our expected force would be based on our current knowledge and understanding, whereas the blue line is the force data. Basically, the procedure was it started at a 0 position, moved to the left, drawing the line through the capstans, and then stopped momentarily and moved backwards. So as you can see, the red line does not match up quite exactly with when it's moving away from when it's moving through the capstans. But on the way back, it does match up quite closely, which we were trying to figure out why that's the case. It could be some issues in our coefficient of friction measurement, could be other things that we don't understand yet, but we're trying to figure that out. Noticeably, the initial drop we don't have counted for, but we do understand that this is just because the angle switches signs, which causes the exponent to become negative exponent, and drop it down, which causes this change, this seemingly instantaneous change in force. And we'll revisit that effect later as well in our next experiment. So most of the time in a weave, both ends are not able to freely slide. One of the ends is fixed. So we then began to look at that case, and to accomplish this, we fixed one end with the force sensor, applied the known force again on the other side, and attached our motion device to our central capstan. We're able to change the angle that way, move it forward and backwards. And this is our data for that one of our data sets for that test. It was a 3-cycle test. So in each color represents 1 cycle. The red line is again our expected value. But as we can see, it matches very closely on the way up. But on the way back, there's this plateau that forms does not match closely at all with what we would expect. And yeah, we're not sure why that's happening. We're still investigating that. And back, you can notice again that our large drop off here, that is again due to the change in sign of the total angle. So then what is our next substance experiment? So obviously there's still some unknowns that we have to figure out in this simple 3-capstan experiment. But after that, we'll be moving on to replacing our rigid capstans with another filament to see how this modifies the capstan equation anyway. If it does modify it, we'll investigate that. And then from them, we will replace our 3 rigid capstans with 3 filaments, see how combining filaments, see if we still observe the same effects we did with the rigid cylinders or if that changes. And then we will move on to our first object that could be classified as a woven structure, probably the most basic, where we have 3 threads interwoven with each other. Yeah, well, I hope you enjoyed this presentation.